Say we have a piston cylinder device that contains 1 liter of saturated R410A at a temperature of 20 degrees centigrade. This piston cylinder system is allowed to slowly expand in a constant temperature process to where our final pressure is 400 kPa. Assuming the process is reversible, we want to calculate the work and heat transfer of this process. To begin, we will rewrite the Clausius inequality for an isothermal process. Our change of entropy between our final initial state is equal to integral from state 1 to state 2 of our heat transferred per our boundary temperature. Or our heat transferred going from state 1 to state 2 would be equal to our mass times our temperature times S2 less S1. We need to determine a few important properties. First, let's look at state 1. We know we have a volume of 0.001 meters cubed. Our specific volume is 0.000923 meters cubed per kg. Our specific internal energy is 87.94 kilojoule per kg. And our specific entropy is 0.3357 kilojoule per kg. Now we proceed to state 2 in an isothermal process. That is, our pressure at state 2 is less than that at state 1, and therefore we are superheated. Our specific volume is found to be 0.07916 meters cubed per kg. Our specific internal energy is found to be 276.44 kilojoule per kg, and our specific entropy is 1.2108 kilojoule per kg. Our heat input, Q, going from state 1 to state 2, will populate our conservation of energy equation. First, we have to solve for our mass before we can solve for our heat input. Our mass is equal to our volume per our specific volume taken at state 1. Our volume at state 1 is 0.001 meters cubed per kg, and our specific volume was taken as 0.000923 meters cubed per kg. Thus, we have 1.08 kilograms of R410A. Therefore, our heat input is equal to our mass times our temperature times the change of our entropy. That is MT times the quantity S2 less S1. We have a mass of 1.08 kilograms. Our temperature for which this is occurring is 293 Kelvin. And our entropy at state 2 is 1.2108, less our entropy at state 1, which is 0.3357 kilojoule per kg. And thus we transfer 276.92 kilojoules into our system. Therefore, we can go back to our conservation of energy equation and solve for work. Our work going from state 1 to state 2 is equal to our heat supplied minus our mass times the change of our specific internal energy. That is, work going from state 1 to state 2 is equal to 276.92 kilojoules, i.e. our heat supplied going from state 1 to state 2, less our mass, which is 1.08 kilograms, times our specific internal energy at state 2, which was 276.44, less our specific internal energy at state 1, which was 87.94 kilojoule per kg. And thus the work done in this process is 73.34 kilojoules.